we are looking at inverses. And so again, we skip 1-4 because it's parametric equations. And we, on the AP exam, do not need to know how to write parametrics. Parametrics are kind of like three-dimensional, but not. It's basically writing function composition. So function composition is actually going to be a part of what we look at today. So we're looking at functions and their inverses. The reason 1-5 comes later in the chapter is because you have to have an understanding of domain and range. You need to understand what makes a function one-to-one. How do we find an inverse? So that's going to be our goals for today, is one-to-one inverse and finding inverses. And then part 2 of 1-5, which will be day 2, is logs, property of logs, and applications. So one of the things we're going to do is talk about vocabulary. I will say things out loud, and it's important for you to understand what I'm saying. So a function, if you hear me use the word function, I am talking about a equation or expression that has a domain in which every x pairs to only one y. X squared and x cubed are both examples of functions because even though they have an x value that repeats y values, the x's don't repeat. So -2 and 2 both go to 4, but the x's are different, therefore still making it a function. The next part we're going to talk about is being one-to-one. A function is one-to-one if each output, which is the range, is associated with exactly one input or domain. So now x squared is not one-to-one because the output 4 goes to 2 different inputs. So x squared is not one-to-one. X cubed is one-to-one. So a function passes the vertical line test. So again, a function passes the vertical line test. A one-to-one function passes the horizontal line test. So graphically, a one-to-one function passes the horizontal line test and states that the graph of a one-to-one function can intersect any horizontal line at most once. If it intersects such a line more than once, then the same y value is considered not one-to-one. So again, x squared, not one-to-one. X cubed is one-to-one. Sorry. Okay. So using the horizontal line test, determine whether the functions are one-to-one. So in order to determine if a function is one-to-one, we need to know what it looks like when we graph it. So you have f of x equals the absolute value of x. The absolute value of x is a V-shaped graph. So again, would the absolute value of x graph be 1-to-1? Is that going to pass the horizontal line test? No, because at several points, we intersect more than once. So f of x equals absolute value of x is not 1-to-1. G of x equals the square root of x. Now in this case, it is just the positive square root. So that means it looks something like that, or half of a side of a parabola. So as x is increasing, so is y. Y is just increasing at a lesser rate. Is the square root of x 1-to-1? Yes. So again, not 1-to-1 and 1-to-1. The reason we discuss being functions and being 1-to-1 are inverses. In order for a function to have an inverse, it needs to be 1-to-1 or come from a restricted domain. Since each output of a 1-to-1 function comes from just one input, a 1-to-1 function can be reversed to send outputs back to the inputs from which they came. So the idea of an inverse is that the domain and range flip-flop. So the domain of the original becomes the range of the inverse. The range of the inverse becomes the domain of its original. So again, domain and ranges flip-flop. So if the point AB lived on the original function, then on its inverse, you would have the point BA. The function defined by reversing a 1-to-1 function f is known as the inverse of f. F inverse in function notation is an f with a -1. That does not mean 1 over the function, it means f inverse. So f to the -1 does not mean 1 over f, it means f inverse. Function composition, we talked about this earlier. Composing two functions gives you x, means that they are inverses. X is known as the identity. So if I compose two functions and they are inverses, then I should get x, and x is known as our identity function. Oh, look, I jumped ahead of my own speech. So the symbol for the inverse of f is f inverse. We say, again, this is not 1 over f of x. And again, if two functions are inverses of each other, then they must equal x. Okay, determine via composition if f of x equals the square root of x and g of x equals x squared are inverses. So we'll start with f of g of x. Which means that we are plugging g into f. What do you know about the square root of x squared? Okay. So it's x, but there's something else that we have to know about the square root of x squared. It's not just x. It's only positive x, exactly. Which means we need absolute values. By having to place the absolute values on that problem, that is not the identity function. Therefore, we're done because they are not inverses. Regardless of what I get with Goff, because f of g of x is the absolute value of x and not x. It is not the identity, therefore they're not inverses. And again, what do you know about x squared? It is what? It is not 1-to-1. Well, since x squared is not 1-to-1, that means x squared does not have an inverse. So x squared is not 1-to-1. When you do function composition, you have to get the absolute value of x. And again, does everybody know why we get the absolute value of x and not just x? Think about if I plug in to f of g of, if I plug in the number -2. If you just simplified that to x without your absolute values, you'd get -2. If you plug it in and you plug it in originally to g, -2 squared is 4. Then you plug 4 into f, the square root of 4 is 2. We don't get -2. We get 2. So the absolute values are critical to the square root of x squared because you can never get a negative answer when you square something. So when you simplify that, it's the whole even, odd idea. You have an even square root to an even exponent, and you get an odd answer here, you must have absolute values. Even, odd. I talked about that last week in one of the videos you should have watched. We can write our own inverses, and again, we reviewed this in our packets, so this should be fairly reviewable to you now, but there are a couple that are a little bit tricky, so we're going to look at some tricky inverses. You can never leave x and y together. That was one of the mistakes I had seen. We tried to leave our answer where x and y were together. Typically, if you have an x and y stuck together, you're thinking GCF. So let's start with something fairly simple. Y equals 4x minus 12. This is linear. Linear functions are 1-to-1. 4x minus 12, if you graph it, starts at -12, goes up 4, and over 1. So that means we have a point here at 1, -8. You would have another point at 2, -4, and at -3, or 3, 0. When you're graphing, all graphs that are linear or continuous must have arrows showing that. So that was one of the issues you guys had on Delta Math, is some of you put dots instead of arrows, some of you had arrows instead of dots, and then some of your dots were open or closed mixed up. So again, it's important to understand a linear function has a domain of all reals. Therefore, you must show arrows indicating that. Now, we talked about the inverse and the fact that the domain and range flip. So on the original, you have the point 0, negative 12. That means on its inverse, you have negative 12, 0. If on the original, we have 1, negative 8. On its inverse, you should have the point negative 8, 1. We're going to solve for the inverse algebraically. So we're going to flip-flop x and y. So you have x equals 4y minus 12. And then you're going to solve for y. So you add 12, divide by 4. And we get y equals 1/4 x plus 3. And again, that y-intercept should make sense because over here, I have the point 3, 0. So on the inverse, I have the point 0, 3. And then I have the point negative 8, 1. Negative 12, 0, etc. If you have two linear functions or any inverse functions, their point of intersection should always be on the line y equals x. All inverses are symmetric about the line y equals x. So that dashed line I have on that graph, that represents y equals x. All inverses should be symmetric about that line. And again, that's coming from the idea of the flipping of the domain and range. So that pretty much summarizes the first half, having to deal with inverses and their one-to-one functions and properties. There are several practice problems in your book that we're going to take some time and work on for the remainder of class today. You're doing 1 to 6 all, and 7 to 23 odd. And that's on page 44.